למה עשיתי תרנון? לא, לא רוצה את זה, זה יש מספיק צורות. אוקיי. רואים את הלוח, כן? בדיקה של מיקרופון, כן, לכאורה, הוא אמור לעבוד. איך אני אדע שזה עובד? כל החיים. נשמע שזה. אוקיי. או, שאלה טובה, כן. וזה לא מחר, זה מחר. לתורת ההצגות? כן. אולי אני מדבר על זה גם קצת. לא, אבל זה לא יותר מתקדם. אני מדבר רק על עידוד כאילו. Okay, so any questions? No questions. So first of all, I made a mistake last time. It's not true that vector space object or our vector space object in the degree of phi of Anders is a vector one. It doesn't work this way. It's not true even over a point. So okay, but let me tell you something which is true. What is K vector space object in the category C? So what is, let's say that C has order product. So we'll have product. So we have so what is a group object in a abelian group object in category C? You know, it's an object in C with a map which satisfies the abelian group axiom. And now we have a field K. So what's K vector space object? So the claim is that it's an it's a abelian group object together with addition structure and action of the field K on the object X. What does it mean? So basically a map from K to O2 and on. And it should, like the action should respect the additive, the abelian group structure on X. And so what does it mean? We have like, so for any element K here or any element K alpha, we have, let's call it now lambda alpha from X to X. And now we have, how do we do it? Yes, we have lambda alpha times lambda alpha. So you know that we apply the morphism on each coordinate, but okay, it's not a set, so it doesn't make any sense, but we can use a categorical property of product in order to define what we, for example, we know on the level of representable functors, we know what we. And then here we have the addition. Or we can first do addition and then multiply by alpha. So this diagram is commuted.
To clarify, you wrote an arrow from K to endomorphisms of X. In which category is this?
Set groups, semi groups. Endomorphism of X is always a same group. We have a multiplication, and this is a multiplicative same group. So any element in K should give me endomorphism of X. X is object in a category, I know what is endomorphism, and I know what is the composition of endomorphism and product of numbers in K, and go to composition. This is like part of the linear space axiom that you know. And now I want it to be to also the other part of linear space axiom that the action is homomorphism of abelian group, so it's commute with addition. So if we take two elements, multiply each one of them by constant alpha, and then sum, it's the same like add them and then multiply them by constant alpha. So this is this diagram, it should be commutative. So it's nice because it basically says us that a category of so what's happening if we work in, say, topological spaces? We'll get our linear spaces, which are also topological space, and the additive group structure will be a topological group structure. And also multiplication by scalar will be a continuous map for each specific scalar. But it will not be topological vector space. So this map will not necessarily be continuous. Or it will be continuous if you take on R the discrete topology. But this is kind of weak condition. For example, if you take R with a discrete topology or R with like the standard topology, they both will be object in this category. While only one of them is a real topological vector space. Only when you take the standard topology. So you don't get the thing you want, and I don't know a nice categorical way to describe what a topological vector space and like take into account topology on the base field. If you take abstract fields, then K vector spaces in topological spaces, it's kind of K topological vector spaces, but you ignore the topology on K. So we're taking a discrete topology on K. But if you want to take into account this topology, then I don't know how to do it. Probably possible, but I have to work harder. Probably possible to do it in terms of category theory. Of course, you can do it. You know what are topological vectors. Questions about this? Okay.
Probably need to start with topological field. Okay.
Yes.
You're right. Your homomorphism from K to endomorphisms. Something like that is important function.
Yeah. So if I have a topology here, so maybe if your category is enriched over topological spaces,
you need to substitute this arrow from K times X to X.
yes, this is the usual definition of topological vector space, and this is correct. But the question, can we do it like an object of some category in some other category? So object of K vector spaces in the category of topological spaces will not give you a topological vector space because you don't know the topology on K. So, but there are things that you can say. Yes, you can say that the category of topological spaces have an internal home structure, have a structure of topological space on each home, and then you can try to use it. But okay, let's not go there now. I don't know it. Probably will be too complicated at this point. Oh. So the second thing that I wanted to say last time and forgot is criterion for representability of a factor. So I think Shachar told you that if you have a factor for your set that maps limits in C up to limits in set, but let's not say it like this. Let's think about it as a factor from a quantifier factor that may all limits. So it's always the other direction, and if f is representable, it maps all limits into limits. And sometimes it's enough in some examples, but sometimes it's not enough. You gave example, it's not enough. So there is kind of general criterion when it is when a function call limits to limits actually have to be representable. And it's not if and only if criterion, but it's working in many cases. And the idea is that if C have, I would say, all limits or all colimits or enough colimits, to be honest, then it is correct. And again, we have here the set theoretical problem. What do it mean enough colimits? But we can say that C is small and we have all the small colimits, and then the statement will be correct, but kind of meaningless because not too much examples like this. And there are some formal way to formalize it. So the idea is that C is not small, but it's kind of generated by a set. One has to explain what has been generated, and then it's have all small coordinates. So this is one of the ways to do it. But for the sake of this discussion, I will just prove this correct, but totally meaningless theorem, or not totally, mostly meaningless theorem that says that if C have all small colimits and is small by itself, then any function that maps colimits to limits is representable. And so by itself it's kind of meaningless, but the same proof give you code statement once you do a person code in terms of set theory. So let's see how does it work. As usual, you basically do the only thing you can. I can note it down so I will not forget. Yes. So we have an object. We want to find an object. We have a function which is also representable, which maps colimits to limits. We want to prove that it is representable. So let's assume for a moment that it is representable. I claim that I can now define the overcategory of the objects that represent F without even know what it is. What is this object? Because what does it mean the overcategory? Category of pairs. S and morphism from S to our function is F, and we have this mysterious X that doesn't really exist here. So what is the overcategory of X? Is pairs object S in C and a morphism from S to X. So I don't know what is X, but I do know what is morphism from S to X. It's just element alpha fx is a set, so sorry, fs.
Sorry, what was it?
X is a wannabe object that represents F. I don't know it exists. But for a moment I imagine it exists, and then I know what is the overcategory of X. It's pairs of objects in C together with a morphism from S to X. Now I can phrase it without saying the forbidden word X. It's just object in C together with element in f of s. F of s is a set, so we can talk about elements there. So let's define it to be the overcategory of the function f. If f is representable, then this is actually the overcategory of the object that represents f. But I can define it always. And now I can take the polynomial over. Let's call it alpha. Yes. SCF. All the elements. And here, limit of what?
We have also limit.
Well, assume now that we have all colimits, or small colimits, but category is small, so all colimits. Now you remember that if the function is representable, then this is the overcategory of X, the representing object. And when you take colimit over something which is actually an overcategory, so you get the terminal object. Yes, the overcategory have always a terminal object. So it's overcategory, it's the object itself, it's terminal object in the overcategory. And colimit over category which have terminal object, or diagram the terminal object, it's just a terminal object. So if it is representable, then it gives a representing function, object, and we can just define the representing object, and then it's rather to show that actually I mean, is equal or as a most of those to the unit inbuilt effect is actually represented by x. So this not exercise, assuming that this thing makes sense, yes, assuming the two have this limit. So in particular, I want this to be small. Usually we discuss only small bodies that make sense. And so, of course, in real life, it usually will not be small, as this will not make sense. So, what you actually do is you will choose some subcategory or subcategory of S of C, and which is small for one thing, and for the other hand, it's enough object that generated those things. And then it also will work, but then it's harder to function. Questions about this?
Could you say once again what is IC class?
This is a unit functor. I see on C choose. We find an object that represents it, and as usual, when you want to prove that something exists, so the hardest part is to find it, and then it's usually rather easy to show that it satisfies what you want. In this case, this is what you want. Okay. Now another theorem of this type says that so when functor is an adjoint functor, or in other words, when it has an adjoint thing, and you probably remember that functor that have an adjoint. So I think it also was in the TA sessions that if a functor have an adjoint, then it have corresponding limits. So either limits or colimits, depending on the fact, on the question whether it's right adjoint or left adjoint. Well, I don't remember what side. We can try to open stuff together, but it was kind of tautology, yes. So you remember this fact?
By have limits, you mean commutes with limits?
Oh, sorry. Yes, there's functor commute with limits, so maps limits to limits. You remember this fact?
I think left adjoint preserves co-limits, right adjoint preserves.
So the left adjoint preserved co-limit and the right adjoint preserved. So now in the opposite statement too, so of course it's not true if you don't have limits at all, because then you start with an empty assumption. But again, if you have limits, or enough limits, whatever game you want to play, and then it is true, and basically you can prove it using this previous representability criteria. So let's formulate it. If f b to b is joined, then no, map leave in, then it has something or the other something. I think left. Well, you basically tell me. Yes. If it is right as a joint, then it maps limits to limits. Did this what you told? You did.
I said left adjoint co-limits to co-limits.
So right adjoint limits to limits. So if it has left adjoint, then it's okay. So we basically know that any functor have left adjoint, but it doesn't know it yet. So any functor we can try to define a star of D, but not a star, sorry, X, but we don't really know how to define it, so we do know how to define this. Yes. This is equal to of y. This is equal to more from correctly. So I would know the functor that it represents. So the functor that it represents, more of them. Okay, wait. If f is less than joint, so f has to be. Sorry, it has a yeah, so this should work like this. So this is f star will
Is right
be
expression for United Way.
what?
This was the image of F, not F star.
Wait. Wait.
By definition, it should probably
Yeah.
morphisms from Y to F star.
Y is element in object in C. So I can't put it up. Yes. If Y is object in C, and then this makes sense. But then F star going to be the right adjoint, yes. But this should be equal to more Y. Okay, so but now it will be co-limit. So okay. Let's write Y to right. Fair. And for now, let's try this and then change it. Okay, so I know, I don't know what is a star of X, but I do know what functor it represents. It has to represent this. Now I want this functor to be representable. So what's the criterion? That it maps co-limits to limits. Yeah, so here, so I want to show that this functor that maps Y to this thing maps co-limits to limits. Now, if f by itself, sorry, if f by itself maps co-limits to co-limits, then f of y, like what the function, this thing, if you now we have diagram on y, yes, we have gamma in C, yes, y is in C. So we have this diagram, f of this diagram, what?
Maybe it should be the another basic of C.
I don't think so. You do what? You are check. So if gamma is diagram in C, yeah. Now functor for some diagram, some shape of the diagram to C. And then limit over gamma over some delta. Sorry, gamma alpha delta and co-limits in a way. Now I want to plug it in, and let's give this functor name G. I want to plug it in G. And then this is equal to a more. F limit alpha gamma F for gamma alpha x. Yeah, just plug. I take the limit of this thing when y is ranging like here. colimit. And now the idea is that limit that more maps. No. Here I should write. Oh, not just gamma. Gamma. Here I should write colimit of gamma. Now f maps colimits to colimit, so I can take the limit, the colimit out, and then I can take it out of the more, but then it becomes but more maps colimits to limits. The more to limit more gamma of alpha yes, and this is by definition the limit of G of gamma. Sorry, so long. But what we get at the end that G of colimits is the limit of G of the object. So G maps colimits of limits. And so G has to be representable, which means that the functor f have an adjoint. Say it from the beginning more accurately.
Yes, did we ever prove that the more functor maps all limits to limits?
I probably didn't book in the class, but so exercise anyhow. Okay, anyhow, it's the definition of a limit, yes.
No, I started to
Yeah,
just
it was one of the definitions. One of the definition of limits was that we know what is the limits in sets, and then we use it to define any category. So colimit is a limit in the opposite category, and then we use it using an embedding in order to define what is a limit and what is a colimit. And we use the notion of limit, so it's exactly one set more maps colimits to it.
Why is G being representable mean that it has an adjoint?
Because when we want to define an adjoint, what we said, we for each object want to define f star of x. Instead of doing it, we just define what is its unit embedding, this G. And if it is representable, then we will say the adjoint is defined on x. So in general, we always have a joint which is partially defined. So to say it is defined, we want to say define in each object. And define on x if and only if this functor is represented. Yeah, maybe this should set with the parentheses. That's how it feels. This is G and this is parentheses. Not parentheses, what they call it? Station parentheses. If in order it to make sense, f star has to be defined. Otherwise, we don't really have. So we have this first theorem, which is criterion for representability, and the second theorem, which is criterion for existence of a joint, or criterion for the functor to be a joint. And we show that the second follows from the first, and in fact, one can take it the other way around. I will not say the details, but if you do believe this theorem that the functors commute with limits have a joint, then the other way around is also correct. Then you can prove this theorem that functor terms origins to limits is representable, and the idea is that you just take f. So if it maps call limits into limits, so what a functor from C op to sets maps and limits to limits, and then it's have a join for the side that you need. F star with the functor from sets to C op. And I see here you take the singleton and see where it maps to. And this object is object in C because C op and C have the same objects. This is the object that represent. I think you should do it for singleton, not for the empty set. Okay. No. So these are my depths from last time. איך אומרים רחובות? Now let's go into group points. So what are group points? You remember a category whose all morphisms are bottom. And now there is this theorem, I don't remember whether called it theorem if G void then gamma is equivalent, not isomorphic, but equivalent to a category to this joint of co-product of following categories BGI this is the is theorem. You choose an object in an isomorphism class of gamma and take its automorphism group. This would be your GIs, and then you have a functor from here to gamma, which is fully faithful and essentially surjective, so it is correct. So one can say that there is no meaning to study group points because the theory of group points is basically equivalent to the theory of groups. But this is not completely correct because, first of all, this isomorphism is very non-canonical. You have to choose an object in each strata, so it may make your life inconvenient. And in each isomorphism class. And also, you have some categorical construction that you can reformulate in terms of groups. So if you formulate them for group points, you can reformulate them in terms of groups, but then you get some constructions in groups that you didn't see before. Yes, which are kind of weird and complicated from point of view of group theory. And maybe the last reason, which we will be maybe later in this lecture, is that when you talk about categories or about group points, we talk about everything happening over sets. Yeah, so the collection for objects, for morphisms or sets, so classes, something discrete with no additional geometric structure. But it also makes sense to do everything with geometric structure. So to do it for category, it's complicated for general category, but for group points, it's not too hard. And so the same way you have topology, you have abstract groups and then you have topological groups. You have group points and you can talk about topological group points. So it's a bit more complicated notion, and one can discuss how exactly define it, more than one version. But and not only topological, you can do algebraic group and Lie group. So for all these versions, you have all these notions, you have group point version. And then this theorem is not true, because then the notion of disjoint union, so it's true on the set theoretical level, but it's not disconnected. And this is why the theory of groupoids is not really well developed and not really so interesting because we always have groups. But once you go into geometric situations, then it becomes very powerful theory and very popular theory. So algebraic geometry, it's called the theory of algebraic stacks. Algebraic stacks are kind of algebraic groups, but not for groups, but groupoids. And you can do it for other complex tools. Less popular there, but it also works there. So I think in differential topology, they usually call it orbifolds. And so there are many names, but okay. And now examples of groupoids. So of course, first example is BG. Okay. Another example, which is very common. So you have an action of a group G on a set X. You can do it in geometric context, and then you have topological group or topological space or whatever. And then you can consider the quotient groupoid in homology. What is this quotient groupoid? It's a groupoid which objects the set X and morphism from X to Y, morphism in this groupoid, yes, X to Y, is a collection of all G's such that Gx equal. Yeah, and then this theorem becomes very, I think, well-known theorem here, that if you have a set, the group action on it, and then first of all decomposing to orbits, and then each orbit looks like G modulo a subgroup, and the subgroup is exactly this automorphism group of a point. The automorphism group of a point in this groupoid will be the stabilizer of the point. Yeah, okay. And this is a very nice point of view. And one thing it gives you that often you do some question when you have basics and group G acts in it. This is very common topic in mathematics. And you think that you care about the group G and the space X, but often you don't really care about them. You care about this group point. Or if you have some geometry, this stack or whatever geometric version of groupoid you're working with. It means that you can replace X by some other player, by some other space Y, and G by some other group H, that's X and Y, and as long as the groupoids are equivalent, and the groups, the question that you study will have the same answer. So maybe the most standard question that you can ask is what is the space of invariant functions of X? So this space you have a natural basis, which are exactly the orbits, and it depends only on the set of orbits and does not really depends on the group on the X. So the set of orbits is a set of the isomorphism classes on the groupoid, so it depends only on the set of groupoid, on the groupoid. So this is maybe too primitive, for example, because it depends only on the groupoid, but it depends on much less than the groupoid. It depends on a set of isomorphism classes in the groupoid. But now we can ask like more complicated questions. So if you talk about shifts over this space X, and you can talk about what are G equivalent shifts. So I didn't define it, but if you know it, you know that there is such an object. And then it's not true anymore that it depends only on the set of isomorphism classes, but it's still true that it depends only on the group. So this is one example. And now another example. Or maybe not really one other example, but okay, so just a general statement that most of the natural examples of groups, in fact, coming from a groupoid when you like specialize it to look in a group, which makes sense because we said that because of the first theorem upstairs, there's not really a big difference between groups and groupoids. So maybe the most basic example of group is a group as n, group of permutation of n elements. So you have the groupoid of finite sets. of sets, but the groupoid of sets. Groupoid of if in general we'll have this notation given a category, the corresponding, כל הבית זה תיק. התיק יש גם תיק.
תראו לי את המחשב אתמול בלי תיק. תודה רבה.
מה שיש בלי תיק, יש מחשב בלי תיק. So if we have a category, we can consider the corresponding groupoid, just all the, we know everything which is not isomorphism. So what is a groupoid of sets or finite sets? It has many isomorphism classes, and so it's equivalent to union of all its isomorphism classes, to product of all its isomorphism classes. X sets, basically cardinalities, but for each isomorphism class we choose a representative, and here we have permutations of these. So basically the same lexicon group as n, but not for one n, but for all n together. And if we consider all sets and not finite sets, so for all cardinalities together, including n. So this groupoid encodes everything we know about Sn. And if you think about it, we don't really care about Sn as permutation of a set of n elements, the set of numbers from 1 to n. We think about it as a permutation of a general set of n elements. And we just choose n because it's a convenient set of n elements, but sometimes it's not convenient. Sometimes you would prefer to work with others. And so this guy is kind of more natural version of the guy in the left hand side, but it's more similar to this guy because you don't choose specific set. The same with the groupoid vector spaces. This is kind of the natural version of GLM. And other groups that people like, ON. So here it will correspond to vector spaces with scalar product. Or SPN, vector spaces with a symplectic structure. And okay, the other groups in this list that if you took a course in algebraic groups or Lie groups or the algebras, you know that they are like E and G and F, exceptionally groups. And there it's not really clear how to find the natural groupoid to attach to them, but at least like about 100% of the Lie groups you have very natural groupoid attached to them.
But for E, F, and G, we have only finitely many dimensions.
Yes, so I don't know what to do here, and do we have something natural that will take some of them together? I don't know, but it's only finitely many groups, not in like 5 years, so we can ignore them for now. Okay, let's make 15 minutes break, which will mean that we meet in 10 minutes. Then we will go to other thing. Huh? 11, sorry. Hello? Isomorphism classes של סט.
בוא נעשה עצמי מותר עצמו.
לא, להפך, קבוצת מחלקות האיזומורפיזם של קבוצות, זאת אומרת קבוצת העוצמות.
יש משהו מיוחד בקטגוריה של סטס בשביל היונד עליהם? אפשר לעשות את זה עם קטגוריות אחרות?
לא ממש, זאת אומרת אפשר לשנות את ההגדרות. התשובה של הום זה קבוצות. אוסף כל הדפיניטים של אובייקט זה קבוצות. עכשיו אפשר לדבר על מושג אחר.
יש לו גם מבנה נגיד, לא יודע, של...
להום, מבנה של גרופואית.
כאילו הום של...
חברה בלית הרבה פעמים. עם הקטגוריה אלפית. באופן כללי יש מושג של קטגוריה enrich over, מאושרת מעל קטגוריה אחרת. זה למעשה בכלל לא קטגוריה, כן? בהינתן קטגוריה ארצית, אפשר להגיד, באופן הכי כללי מבנה מונואידלי, אבל לא חייבים להגיד את זה, אפשר להגיד עם כפל, שמוגדר בכפל, אפשר להגיד מה זה קטגוריה אלפית, enrich, למה הכל לא עובד? שהיא enriched over C.
ואז זה נשמע הגיוני, זה בכלל מה שקורה.
זה לא, לפני שנייה כחול לבן.
וזה אתה רוצה.
D enriched over C. עכשיו, באופן כללי המושג הזה, קטגוריה enriched over C, זה לא מקרה פרטי של קטגוריה, זה מושג אחר.
אוקיי.
קבוצה של אובייקטים, או מחלקה של אובייקטים, ולכל שתי אובייקטים, אובייקט ו-C שנקרא ההום ביניהם, והעתקה קומפוזיציה שמקיימת את כל האקסיומות, בשביל לנסח אותם אתה צריך מכפלות ב-C או משהו אחר שישיג מכפלה ב-C.
אוקיי, שאתה נותן להום מבנה של קטגוריה אחרת.
ואז היונדה יהיה במונחים של C. עכשיו, אני אומר שבאופן כללי זה לא מקרה פרטי של קטגוריה, אבל בדרך כלל הדברים האלה הולכים ביחד. בדרך כלל ל-C יש פונקציה של פונקטור לסט, וברגע שיש לך פונקציה של פונקטור לסט, אז לכל C קטגוריה יש גם מבנה של קטגוריה, פשוט אתה מפעיל את הפונקציה של פונקטור.
אז משהו מיוחד בקטגוריה של סט זה פשוט שיש לך מבנה של יש לך תמיד forgetful functor מ-C ל-S.
לא. מה שמיוחד בסט זה שהום הוא קבוצה. כל תורת הקטגוריות היא בכל זאת מושתתת חזק מאוד על תורת הקבוצות, היא לא מנותקת, אולי צריכה להיות דרך לנתק אותה ממנו, במובן מסוים לסוף קטגוריות קצת מתנתקות, אבל גם פשוט בונה מגדל עם הרבה קומות, אבל בבסיס עדיין יש לה קבוצות. אני לא מכיר דרך להתנתק לגמרי. ההום, אנחנו צריכים מסוגלים לדבר על מורפיזם לדברים בודדים, נגיד לכמת עליהם לכל מורפיזם קיים משהו, אנחנו כאילו נפטרנו מהצורך לכמת על איברים באובייקט, אובייקטים, נקודות, דברים אבסטרקטיים, אבל לא באמת נפטרנו, העברנו את זה פה את הצורך הזה למור. עכשיו אפשר גם שם להתחכם ולהגיד, בשתיים קטגוריות, קטגוריות גבוהות יותר, המורפיזם זה קטגוריה, גם אנחנו לא לוקחים איברים בודדים שם, אבל שוב, בקושי זה יבוא בשלב הבא.
זה לא אבל המטרה סוג של תורת הקטגוריות כזה, להתנתק מתורת הקבוצות ולעשות כזה...
לא, המטרה בסופו של דבר באה משאלות קונקרטיות, היסטורית, תורת קטגוריות, באה מטופולוגיה אלגברית. הבינו שיש משמעות לדבר על פונקטור, כן? הבינו שיש... שכל מדרג, הומולוגיות ומטופיות, הם תלויים במרחב הטופולוגי ונותנים לנו, כאילו, מכניסים מרחב טופולוגי ומקבלים חבורה, והתלות הזאת היא לא סתם מפונקטור, כן? כשהגדיר מה זה פונקטור, הגדיר מה זה קטגוריה. אחר כך תורת קטגוריות הלכה להרבה מקומות, בדרך כלל בכל זאת המטרות הן לא איזושהי מטרה אבסטרקטית כמו להתנתק עם משהו אלא לפתור בעיות, אבל כן, זה גם היה יכול להיות, אני חושב שזה כן היה יכול להיות נחמד להתנתק קבוצות יותר או לגמרי או משהו, אבל לא יודע. אולי אני רוצה סוכר בזה. אבל עכשיו אני לא מבין, עכשיו אני צריכה לדבר של שאלה?
כאילו, אני לא כזה הבנתי
אז יש כאן שתי משפטים שהוכח, כן? אחד זה קריטריון ליציבות, ושני זה קריטריון לקיום צמוד.
אוקיי.
והקריטריונים נשמעים מאוד דומה, כן? פונקטור יציג, לא אמרתי, אם פונקטור מעתיק כל גבולות לגבולות, פונקטור לקבוצות, פונקטור קונטה וריאנטי לקבוצות, מעתיק כל גבולות לגבולות, ויש מספיק כל גבולות, אז הוא יציג.
ואז פה בעצם השתמשנו בזה.
בשביל להוכיח את זה, השתמשנו בזה. ובסוף אמרתי גם הערה שאפשר לעשות הפוך, אפשר להוכיח קודם את זה, ואז להסיק את השם. אבל לא הוכחנו באמת את ההוא, כי הוכחנו אותו ובכלליות שהוא לא מעניין.
אז פשוט אמרנו פה ש-G משמע בגבולות.
ש-G משמע בגבולות, ולכן הוא יציג, ולכן F, הצמוד של F מוגדר על האובייקט הספציפי הזה, וזה נכון.
בסדר.
ככה אני אושת בהיי עכשיו. אני יודע, אבל it's not like I'm gonna acknowledge it if I'm not high. כאילו, ייחוד זו של נמלים. זה ממש משהו תסורי.
הרבה דברים שבשביל דבר שאנחנו אומרים, זה לא מתעסק ממש אבסטרקטי. אני חושב הרבה שלך כמו פיזיקה, כבוד ואובייקטי. משהו להגיד משהו נביא, מה זה? כמו פיזיקה, זה גם שהוא או פיזיקה. יש גבול לפעמים קצת להרכיב, זה עושה מידע, אבל זה יכול להיות מתחיל לדבר על כל כך קצת חמוס של טרנספורמציה. כל הסוף של טרנספורמציה של מורד. לא ספרות כמתית של הכל וכל יותר לכל היסטוריה. שום לעשות שלה, לא ספרות לכל זה דירק להפסיק. לא יודע.
Это мы не узнаем в следующий. Больше речи не покинули.
אפילו מתכונן שיש יותר מדי assumptions.
לא ספרות שלה. לא ספרות שלה.
Как ты можешь?
יש לנו קצת לעבוד איתו. זה פשוט. או כאילו זה בריפינגס זה מדהים.
А почему тебя это не удивляет?
שזה זה להשמע שאתה
יש גם אומר naturally isomorph.
כן, נכון,
It's naturally isomorph. canonically isomorph.
Все просто измен.
יש isomorph, יש canonical.
Сейчас минимум 12. По крайней мере, так написано.
מילים אומרים
Как сказали, блин, есть
מתי הולך להשתמש באבסטרקט נינסנס? אתה מכיר את זה. זה כאילו עכשיו כזה בכל רמה טריוויאלית. כלומר, by due to abstract nonsense. This is true.
אבל כבר אתה אמור להרגיש תמונה בסטרפיקון שזה ברגע שאתה פשוט אוהב את ג'ק דבר אתה חושב שאתה תהיה שם חיבור זה לא מיליון
כן.
וגם פה אני יכול ללכת וגם פה אני יכול ללכת אז לא משנה פה אתה אמור להרגיש את הנונסנסיות נכון אבל זה פורמלי אבל אתה מרגיש
שפט דלגל
כאילו איך הגענו ממתמטיקה כאילו של לא יודע, מוטציות וזה, ואז הגענו לדף אחרי דיאגרם, כאילו וזה לשלב הכי היי לקושוס, מה עשינו? כאילו זה היה משהו בדרך.
לא, אנחנו טופולוגיה וגם אנחנו מתחילים מטופולוגיה, ואז שום מצב הכל זה דיאגרם שיסים. אני התחלתי לעשות דיאגרם צ'ייסינג וטופולוגיה ואני חושב שזה פשוט כלי אחד בתוך העולם הזה. יש את הכלי.
על איזה כלי מדובר? על איזה כלי מדובר?
כאשר עשיתי טופולוגיה בריט ובסוף כל מה שעשיתי זה דיאגרם צ'ייסינג חשבתי אוקיי הנה כלי מגניב נשתמש בשביל הנושא הספציפי הזה ועכשיו כאילו אני מבין שדיאגרם צ'ייסינג זה כאילו הכל.
אבל זה כלי שמשמע שהמון
Я уже типа неделю обещаю.
אבל בתורת הקטגוריות זה...
Возможно, если бы хотел себе. Спасибо.
כן, שאל אותי מה אתה חושב. זה הצגות של חברות כתיית אמרתי.
כאילו ג'נרטורס וזה. אצל הצדדים?
לא, אז חבורה סופית.
אוקיי.
ויש לה צבוע.
לא פרזנטיישן אלא רפרזנטיישן.
יש מרחב וקטורי והיא פועלת אבל. כן, כאילו כמו שיש חבורה שבולטת קבוצה, היא פועלת על מרחב וקטורי. על ידי בולטת קבוצה.
מאוד רלוונטי להרצאה.
כן, אז זה סופר מודל. כאילו כזה בחיים הבאים.
כן, כן. בג'יגול הבא, אני לא מלדים שהוא מאוד מבין.
לא, תורת התשובה זה עדיף לא לכתוב בחיים הבאים. Okay, so can continue. Okay, so now I want to do example of limits of categories, but in case of groupoids. Limits of groupoids. In this example, that when you do it in groupoids and in groups, you get very different answers. So we have the bad one. Oh, this is the good one.
You should throw the bad ones away.
אחר כך נשאר לי כלום. גם אלה... BG to B, BH to BG, BH2, H2. And let's say that the maps between HI to G are embeddings, and you want to compute the limit. So this is a special case of limit groupoids, which basically comes from group theory, so we kind of not expect to get something new. But the limit here, since we do limits, the notion of limits of categories is not limiting a category, and anyhow it's a different setting of groupoids, so it's not the limit of groups, but something else. So let's see what is something else. The idea is that we want to take object here that are such that the images matches here. But when we say matches, we're not allowed to say equal anymore. We're not allowed to say isomorphic. We need to know what is hidden. So object here there is only one, and here also only one. And the images here, of course, would be the same. There is no question. But there is a question: how are they going to be isomorphic one to the other? Well, we can take the identity, but we don't have to take the identity. So the set of objects, so let's call it X. Oh, the set of objects of X. So what is? Points. What? 2 points. Oh. So there's only one choice of point here, only one choice of point here. So 1 point, we'll just ignore it. They're going to be isomorphic, but the only question that we need to answer is how they're going to get. So the set of objects here is the set of the ways those two guys going to be isomorphic.
We have G isomorphism to G, so
Object here, so, and isomorphism between the images, it means an element in G, isomorphism of a single object. And now what is a set of morphisms? So given G1 and G2, what is a set of morphisms? So we have object here, and then another object here, which is the same one, of course, and another object here, same one. So G1 and G2, in both cases, just the same object here. And now they satisfy some condition, but now we want them to be isomorphic, or we want to find morphism between them, so it means that we want to find morphism for the only object here to itself, and morphism from the only object here to itself, such something going to be satisfied. So before something is going to be satisfied, so where is the data living in? What is this morphism from the object here to the other object here and the object here to the other object here?
H1.
H1 and H2 beside H1 times H2. Now let's see whether we can say what has to be satisfied. Do you have guesses? What has to be satisfied?
Or something like images of H2 and H1 after the multiplication must give something which carries G1 to G2.
Very, very correct. So, for simplicity, I assume that H1 and H2 are embedded to G, so that's subgroup, so I just images H1 and H2. But we're not really multiply them one with the other because each of them, one is in the target and one is in the source. So we have to write it like this, H1, G. I think here we have to write H2 inverse, but it kind of depends on your convention. But since it's a groupoid, then there is no really difference between morphism to one side to the other side. The natural rejection, the inversion. So I think this is, like, depending on your conventions, like this is a more convenient way to write it. So if you want, you can write it like this. It's kind of resembles the commutative diatom, so we'll try to do it to explain it. But yes, so you take H1, take H2, and together they have to move G1 to G2. So this is a very good guess, and let's see why it actually works. Let's try to see. So what do we have? Let's put a name here. F E. So we have only one object. We have F of E. And so we have
another name, not G. Maybe
Of-
F prime.
not H also, yes. Okay.
F prime.
Okay. F1 and F2. Yes. Okay, so what do we want? We want with this diagram of PT maps by H1, or maybe call it PT2. The point, yes, by H1 to its side. And now we can apply
Maybe H2.
F2 by H2 to space. We can apply F2 to both sides of H2, but it's going to be just H2 as an element of G. And also we can do the same with PT1. F1. Just repeating now the definition of elements that we had, and remember that there was some music diagram. F1 PT1, F1 H1. And now we also have vertical arrows. So we need to decide where the arrows are going. So think here we have G, and here we have G. And I want this diagram to be committed. Yeah, when we say what is morphism between, I don't remember what we say. So the object is a limit are sets of objects in each category.
Doesn't mean
In fact,
G1, G2.
what?
Just generic G.
You're right. Yes. So yes, it's different one too. There's a map is from one. Yes, so the object in the limit is like quadruple, object here, object here, object here, and isomorphism. No, like 5 things. There's whatever. Top. Object here, object here, object here, and isomorphism from the image under F1 to the object here in the image under F2 to the object here. So in fact, it's not exactly G. It should have been G times G, but we can cheat. Yes. So like in set theory, when we take fiber product, we don't really need this triple point here. Say, okay, we can assume without lots of generalities, and this triple point is just equal to the image by F1, but the other point we can't assume it's equal to. And the image by F2, we need to find to give this isomorphism. So this is MG on G1 on G2. So now we have two objects, morphism between them is morphism between each of the corresponding objects. So we ignore this one and just look at this morphism and see that from P1 to P1 and P2 to P2, such that after we apply our functor and such that this diagram is smooth, yes, we apply the functor on the morphism, we get these errors, and we apply the two. So yeah, we had to be more accurate, we had to do it with the third object here. We choose to ignore it, and maybe otherwise we would have two triangles instead of one. It was square.
Is this something which is called homocategory?
What?
Is this something which is called homocategory of two functors?
Comma category? Yeah. Maybe, I don't know. We called it the limit of, in this case, fiber product of these two points or this. Okay, but now the funny thing that happened. We started here with groupoids that came from group. But sometimes it's called connected groupoid with a single isomorphism class, or the way we did it, we just took a single object, but it's equivalent to something, to anything with single isomorphism class. But what did we get here? Does this have a single isomorphism class? How many or what are the isomorphism classes of this groupoid?
Like two-sided cosets.
Double cosets.
Double.
So in group theory and representation theory, it's a very common object. You start with the group G, and you have two subgroups. It can be the same group twice, but sometimes it's two different subgroups. And then you consider double cosets. Cosets, you all know what it is. And double cosets, so you're allowed to act with one group one side and with the other group on the other side. And the set of double cosets, so if the group is commutative, then the double cosets and single cosets are the same, and it's kind of single-minded object, just a quotient. But in general, the set of double cosets is complicated set. And moreover, so our group here, of course, there's a new groupoid here, X. We can also write it as a union of BGs. But in order to do it, we need to choose a representative of each double coset. Sometimes it's done in representation theory. If you want to formulate some statements, then you don't use the language of groupoids. Then you kind of feel that you have to choose a representative in each point, in each coset. And then the GI, so who is I here? I arrange this over all the double cosets. And the GI is going to be the centralizer of this coset, and I always forget. So I will write something which is 2 with probability 50%. It's always 2, but like, okay, either isomorphic 2 or like the next, you always can choose an isomorphism. One, let's call it G. Intersection. So stabilizer of a point. So this is a quotient groupoid. So the fiber product of these two groupoids is a quotient groupoid of G modulo the two-sided action. And then the quotient groupoid is equal to union of BGI, when GI are the stabilizer of the points. And stabilizer of the point, we need to choose a representative, so GI, G. and then we take this intersection. So not the genuine actual the original intersection of H1 and H2, but you have to conjugate one and intersect with the other. Of course, you can conjugate the other and intersect with the first, and you get isomorphic things. And of course, this depends on the choice of the representative. But if you choose a different representative, you get something that conjugated to this. Yeah, so this construction, you basically see it in representation theory a lot, and maybe next lecture, this time I will explain where we see it. But usually you see it not in terms of groupoids, just you started with two groups, and then you get you have this question of double cosets, and you know that when you analyze double cosets, for each double coset, you're also interested in this. And this occurs kind of naturally when you do the fiber product of groups. So questions about this? Okay, so since this construction occurs naturally, at basis, it occurs also in several different ways. And this is exactly this typical case when you have equivalent groupoids, which are not which are not the same. So the equivalent quotient groupoids, which are coming from different quotients. So we have this quotient groupoid, G modulo H1 times H2. So this is a quotient groupoid where G is just a set, not a group, and H1 times H2 acts on G using this action. H1, H, H2 acting on G equal to H1, B, H2. And here we have to put zeros, otherwise it will not be an action. This is one groupoid. Second groupoid, we can take G modulo H1. And we can take here the quotient groupoid, but we just can take the set G modulo H1 and consider that a set. Because if you take the quotient groupoid, we see there are no automorphisms, so not well sense. Modulo H2. And here we take the quotient groupoid, because on G modulo H1, we have an action from the other side of H2, and then we can quotient by this action. So it's kind of tautological that these two things give you the same quotient groupoid, but even here, so it looks very similar, yeah, H2. But even here, this set and this set are very different sets, and this set and this set are very this group and this group are very different group. But now the third example, which is most fun. So of course there is another example with let's look here too, but one, this is not interesting anymore. But the third example, which is most fun, which is kind of mixing those two things together. You take this, you multiply it by this, and then you quotient this. So this is a set and this is a set. It's not a group. But then you quotient it, take quotient groupoid by the diagonal action of G. G acting both, so it takes the diagonal action of G. And the statement is that all three things are the same. And it's very convenient to know in representation theory. So when you do, for example, functions on G which are invariant with respect to size action, it's the same as taking H2 invariant functions on G modulo H1, and of course the same as taking H1 invariant functions on G modulo H2. And it's the same as taking kind of matrices, yes, functions on the product of the two spaces, which invariant with respect to diagonal action.
I think that's exactly what we did yesterday.
In Dima's course, like it was on this record before. So in terms of functions. And here you can see like the real reason, because the groupoids are the same. the groupoids are isomorphic. And by the way, when I say that groupoids are isomorphic, sorry, not isomorphic, equivalent. So often you construct the equivalence in a natural way to one direction, and then you just know that it exists. The inverse exists using the axiom of choice. Here, if the groups are fine, there's not too much choice to make, but yeah. And you sometimes, like, I'm not sure, but maybe when you go from here to here, so sometimes you have to compose several equivalences that go into different directions. Because you know that you can do it, but the composition is not canonical in any direction, but still it comes from canonical equivalences in the middle. Here I'm not sure whether you need it, in what cases you need and what not, but maybe yeah, for going from here to here, I'm rather sure you will want to go through here, and the directions will not confine. So yeah, the natural map is from here to Q. Yes, from G you have a map from G to G modulo H1. The other way around, you have to choose. So from here to here, you don't really have map. You can choose the map and then go back towards here, but it's not canonical in any sense. But you have a canonical equivalence that exists and canonical equivalence that exists. So these two guys are canonically equivalent, although there is no canonical equivalence between them. But the knowledge about the equivalence is canonical because it's coming from two canonical equivalences.
Could you once again say how G acts on the product?
On each coordinate separately.
By just multiplication by G.
For lefties.
Yeah, should it be G inverse on the left and G on the right?
Not the way we wrote it here. So if you take the both quotients from the same sides, then G are on the same side. But we use the fact that we're working with groupoids here. So
H2 acts not by inverse.
What?
H2 acts not by H inverse, but
This is just a quotient by a group. So you're right that H have to act by inverse H1 and H2, but you don't really care. Yes, it's just quotient by standard, like you have a standard notion of right quotient by a subgroup. We have a set of right quotients, yes. It's called right quotient. If the group from the right, then it's right quotient, yes. Now this collection of right quotients, this collection of right quotients, G acts from the left on the collection of right quotients. Here, the same thing. So here we interchange them, and here we choose that H1 acts on the left and H2 acts on the right. But this is isomorphic to a situation when they're acting from the other way around, because we have an isomorphism between a group and the inverse group. As for any group, we can define the inverse group, which has the same element as the product going the other way around. And these two groups are always isomorphic because the inverse map is isomorphism between the group and the inverse of opposite group visualized coordinates. So I have G and G op. In group theory, even not category theory. Yeah. G op is this group with the same elements, but the product going the other way around. And here we have this isomorphism. This is general for any group. And this is why doing these quotients or taking them the other way around in this isomorphic groupoids. Yeah, so all these groupoids are equivalent but not isomorphic. Yes, if we consider the one category of groupoids and they're different, they're not isomorphic. Okay. So now let's make it even more similar to the previous course. Let's talk about representations of group. So what is the representation of a groupoid gamma? And one thing that I didn't say. So this was about fiber product for very specific groupoid for BG, but fiber product for general groupoids is not much different. Yeah, so general groupoid look like union of BGs. And then basically, so you have a set of isomorphism classes, and basically you start with take fiber product of these sets. Yeah, one, two, delta. So you can write each of them as union of BGs, and then over each. So first of all, everything splits over delta, so we can take this co-product, this joint union of all isomorphism classes of delta, and analyze everything with the case of delta is single BG, and then take the co-product of the results. And if delta is single BG, then you can run over just all pairs, isomorphism plus here, isomorphism plus here, take the fiber product, and take the co-product of all such pairs. So all the action happen in case of just one and one big in the case of the diagram that we said before, that each of the groupoid is the PG. So you can now understand what is fiber product in general, and that you remember once you know what are fiber product, you can express any limit in terms of fiber product. So now you can compute any limits of groupoids, and you know what's going to be the answer. But in any case, the basic operation is this fiber product of these two guys. When you actually have a splitting situation, you start with things which are kind of one point, but since it's an automorphism, this one point splits to many non-isomorphic objects. Okay, so what's the representation of the group? Combination. Presentation. Gamma in Anton Gamma with oops. So why this definition makes sense? What happens if gamma is Bg? And then representation of gamma is functor from Bg to vect. What is functor from Bg to vect? So it looks stupid at first glance. We just need to determine where the single object goes to. So we know in just a vector space. But there are automorphisms of this single object. So we need for each element in G to give automorphism of the vector space. And it of course has to be homomorphic. So what we got is representation of G. So example, gamma equal Vg. Then gamma equivalent to G, so meaning make G to any action of group G on a vector. And so I defined what is the representation of a groupoid, but it is a functor, so the collection of all functors exists forms a category, so the collection of all representation of a given groupoid forms a category. And if the groupoid is Bg, then this collection is a category of representation of G. And in general, what you have is not much more information. It's just product of category of representations of G for each of the isomorphism class of the groupoid. So studying representation of groupoid doesn't really give you more information than studying representation of a group. So we will usually not study too much because you already know everything if you know group representation. On the other hand, it does give you a new perspective, which can help you, which I will try to show. אוקיי, אני רוצה עשיתי עכשיו. מה האחרון? זה האחרון, כן? So in general, in mathematics and in category theory, if you can assign to each object something, in this case theory, now you have more freedom of the two objects. You want to see how these guys relate. So if you have our case gamma delta and the functor between gamma and delta, when we have the category of representation of delta and category of representation of gamma, we can ask what is the relation between them. Yeah, so in general, we could have expected the assignment that taking a point to a category is functorial, but since it's already in higher categorical language, we start with a category and split a category. It's higher level of functoriality, so it's a bit more complicated. So we'll do it only in concrete examples for now. And what we have, so one thing we obviously have here, which is a pullback. So we can define like this functor between 2 points and f upper star. Oh, so f upper star is a functor from representation delta to representation. So how we define f upper star of some representation O is a proposition first apply f, then apply. So it's a pullback of representation of group points, and it generalizes the notion of pullback of representation of groups, which you know based the mostly two important cases. When you restrict your representation to a subgroup, so you pull it back with respect to the embedding of the subgroup to the group. And another case when you have an onto map, a kind of inflation of representation. If you have onto map from G to H and you have a representation of H, you can also consider it as a representation of G, just that factors through H. Both of these constructions are a special case of the pullback expansion. But once you have functor between two categories, you can ask whether this functor has a job. And in fact, we discussed it in much more general context. We discussed the notion of Karp extension, but in this context, it's really more similar to the adjoint to the pullback of representation. So this functor can, in fact, have two adjoints that are called something like this. One from the right, one from the left, because I don't remember, which is a push forward of representations from of gamma to delta. So let's start with analyzing these two adjoints in case of groups. So do you know, I think we did have this example, what is the adjoint of this functor in case of groups when we restrict from a group to subgroup? What is the adjoint? Induction. In fact, we have two induction. We have big induction and small induction. They're going to be exactly the left adjoint and the right adjoint. Well, I don't remember who is who. So let's define the induction. Induction of O for subgroup H and G is a collection of all, say, functions from G to O. Now we'll consider as a vector space. Such that, and then I'm always confused. F of G times H equal to H, probably with inverse, acting on F of G. So this is when, and then we act from the left. Of course, we can do it the other way around. So this condition can be from the left, and then the action will be from the right. But we can choose whatever we want. And small induction is basically the same thing, but you also give other conditions that these functions have finite support. And you already see the like what is function from G to O. It's a product of many copies of O, G copies of O. And what is function for with finite support between G to O? It's a direct sum of many copies of O. And the direct sum is co-limit, and the sum is and the product is limit. So this is going to be a joint for one side as a limit, and this for the other one side as product. Obviously, for the right.
So could you rewrite it with group algebras? Like one of this
With tensoring with group
Yeah.
algebras. If you
One
want,
of
you
the
can
tensor
write
is
it like this,
the
or
option.
both tensor over the group algebra of H with the group algebra. But this is only for, I think, small induction. Small induction, because group algebra is when you take functions with finite support, otherwise it's not an algebra, you can convolve them. So, okay, so it's
the
not.
holes. Yeah, G.
Yeah, probably yes.
K of H invariant holes.
Yes, probably right. So over H, but what direction is things like this? K of G over H over K of H, let's say.
So how embedding works in this case?
That works so well. Oh, you do have duality, yes. So home between 10. If you have V tensor W, V star tensor W is embedded inside home V W. These are five rank maps here.
Yeah.
So you have an embedding. Yeah, so you have an embedding like this because this guy is self-dual, it comes with a basis. No, it's not self-dual. No, it's not self-dual. But okay, you have an embedding from K of G to the dual space. Will it help? Yes. And then this is embedded the same with here you put star, and then it's embedded here. Okay, whatever, it's not really part of what I wanted to say. So, and these are induction and small induction, which are both adjoining to induction. What happened with the other example when the map is not embedding, when the map is onto? So we have this inflation starting with we have a map formula. The column mission. Oh, what is the mission? So where G maps to A. לפני שנייה זה עבד. אני לא שחררתי אותו, זה לא עבד טוב. G maps to H, take on the map. We start with representation of H, we can inflate it to representation of G. here. And יש כל כך. One second. So we have an onto map from G to H. We have representation of H, we can inflate it to G. What is the adjoint function? Oh, the two adjoint functors.
N is kernel. Or
What?
could you say once again what is N?
N is a kernel of this map. So this is kind of exact sequence. Exact sequence of groups, which is not really a category, but a category. So you have an onto map here, and it's a kernel. So what is a joint factor? I think we had exercise about it.
Which one? For which one?
The inflation. So we'll have P plus R, H, G, kind of restriction, but in case of quantum mechanics, we call it of inflation. You take a representation of H and inflate it to be a representation of G, so it's the same. This basically the same representation, just consider as a representation of G. Or what is that joint function? What's the exercise about it, no? Okay, let's see what we can do. We start with the representation of G, and we want to force it to be a representation of H. But it's not.
Actually, formulas with group algebras works well independently.
Probably yes, but let's do it without the formula. Let's do it in this complete case. So we have a representation of G. It's not a representation of H. I would force it to be a representation of H. Why it's not a representation of H? Because two different elements of G, which maps to the same element of H, act different. Or in other words, elements of N act non-trivial. How we force it to act trivial?
Which universal property we want to satisfy?
Either right adjoint or left adjoint. So,
Maybe
to
we
choose.
take the quotient. The
First
the-
rule.
oh, fourth vector plate.
Okay.
Oh, yeah, but by what? What you want to do?
Well, we glue together all the orbits.
So if you do it like geometrically gluing together orbit, it's
Well, you stick the span.
okay. Span of what? So we're walking in a category of vector spaces.
Yeah.
If we would walk in a category of sets, then exactly this will be correct. We take
No,
The
so
set-
you take some element B and or you take the span of NV. Your N is big N.
NV, it's not exactly your NV. You don't really want to kill it. You don't want NV to be equal to 0.
Why?
It's not the complete answer, it's almost an answer. You run over N in N, but this is not your enemy. You don't really want to kill it because you don't want it to be 0, as you want the action of
You want
N
them to be the same.
the same as both
as B.
V.
Yes.
So who is your enemy?
V.
No, you don't want to kill V, you don't want to kill NV, but who you want to kill?
And B minus V.
X.
Yeah, that's what.
That's it. So now it's important, yes? So you take this functor, take it from V, you kill all, so you start with V and kill all the elements which look like NV minus. But this is half of the answer, it's one of the adjoint functors. I don't remember what side. The other one is even simpler. Instead of killing, you can just choose the ones that you like. No other limits. So what's the other functor? You have a vector space V, and you have a problem that N does not preserve the vectors V. Changed. So one way to solve this problem is to kill the difference. Another way is just ignore the cases when it doesn't change it, and once it turns out the cases it does change. Which are exactly the invariant vectors. This kind of simpler notion usually is the notion of probability, and this is called the notion of point. And both of them are going to be, so both of them have a structure of representation of G. Sorry, of H. So in fact they have a structure of representation of G, because G preserves the vectors of this type, because N is normal, so G preserves vectors of this type. Here also G preserves invariant vectors, also because N is normal, other way. Preserve. But okay, it's have a structure of representation of G, but N acts trivial, so in fact it's a representation of H. So both of them have the structure of representation of H, so we've got functor from the representations of G to the representation of H. And these functors are joined to the inflation functor or Gesher functor or pullback functor. And as usual, you can see that this is some kind of a limit construction, and this is called yes, invariant objects are a limit of certain diagram with the right diagram. In both cases, the diagram is the same. Take V multiplication by n, 1, 2. Now you have this diagram. And when you take the limit, so the things that are going to be here, so what is, oh, this is not good enough. No, it is good. Have an initial object. So I was going to have an initial object. Because I read it the other way around. Okay, let's start with co-limit. Co-limit we see, and the object is here, that all these maps factor through it, so it should be map. It should be a quotient E, quotient space of E, W, such that no matter what n you're going to, you get a commutative diagram. And so here one of the n is identity element. So going directly to this identity. Going directly to W going to be the same as going through any of these guys. And which means that you have to kill all the elements of this guy. So and limit the co-limit of this diagram and like this. And limit, to get this, you can get limit from this diagram, but you have to be careful. You need to read this diagram oppositely. How do you actually do it? Yes, it does. Right, it does. So it's different diagram. Kind of the same diagram, but you write it to the other side, and then the limit of this diagram going to be the invariant, so the limit W extends here, that no matter how you send it to V, at the end you get the same. So the limit of this diagram is invariant, and the co-limit of this diagram co-invariant. And this will give you a joint, so right, a joint is usually limited, if I remember correctly, so it means that this guy, right, the joint is still doing this. Oh, we have 60% probability for being right. Slightly more than 50. Okay. Now, this was one example. What happens for general maps of groupoids? So you can basically repeat the formula for kind of extension that we study. But let's see. I think basically is rather simple. So first of all, it's either. So we have general map between groupoids, but each groupoid needs a coproduct of PGs. So if I have the classes of one groupoid, as I have the classes of the other groupoid, we have map between them. So the first thing that we see is that we can run over the isomorphism classes in the target groupoid and everything, analyze everything to each isomorphism class separately. So we can assume a functor is from coproduct of the BI to the here in a single thing, so a representation of this groupoid, just a couple of representations of each class in the target, so we know what to do. And here we just take the push forward with respect to each of these maps, which we already know what to do. And then take either the direct sum or the direct product, depending on whether we're doing this push forward. This should correspond. This equal to direct product. And this direct sum. of yes, of I think the right adjoint product and the left adjoint is that. Okay, so now we know how to push with respect to map of cuboid and pull with respect to maps of cuboid. Okay, so the next thing I want to skip, no, maybe I will only partially skip it, is co-limit of cuboids. So I tried to prepare, but not yet. But I will say one example which I probably said last time. BH or BG, sorry. Web diagnosis. BG1, BG2, BH. And we can assume that H is a subgroup, but you don't really have to. Then here, when we do push out, we get B, B, G1, amalgamated product over H, BG2. And this I think I said last time, and it is an exercise, it's rather easy. I hope so. And so unlike limits, where we say that basically the case of fiber product is of BGs is enough, here it's not enough. Why? Because if we have the point, so it might be that here we have several isomorphism classes, and they map like with sets. When we take push out of sets, if we take push out not over, if we take push out over a single point, and the maps are embedding, and then we just take how do you call it? Okay, yes, just glue the point. But if it's more than one point, then we can have two different points here that maps to the same point here, but to a different point here. And then we kind of have to glue things together, and it's not necessarily transitive, so we even on the level of isomorphism classes, it becomes complicated. And it's even more complicated when we ask how to do it in cuboids. So I try to do this exercise and didn't do it yet. So you can also think about it next weekend. I will start to think it next weekend, and we can discuss it next time. Okay. So, allora, the last topic that I promised is what happens when we start to talk about groupoid objects in some category. So like we can do group object in a category, or any category you can do like C object in D. We theoretically can do it for the category of groupoids. So formally we can do it for the category of groupoids and then get a category. But the category of groupoids is not something that we like. Because groupoid is higher categorical object, we want to discuss the two categories of groupoid, and we didn't do it yet. But on the level of objects, it is correct and it does work. So what is a groupoid object in a category C? So any guesses? Okay, let's do it. Like with group object. So group object. So groupoid with two sets, more and orb with two maps. So yes. And composition. So what is a groupoid object in C? It's two objects, more in our category C, and two morphisms, source and target. And now I want to say that we also have composition and the axioms of a category or the axiom of a groupoid. And then there is two ways to do it. The hard way, just to say all these things and write the axiom of groupoid. So maybe composition I can say in any case. So more maps. So solve here maybe solve here more target of. So here we have more 2 So the fiber product of these two guys. This is Cartesian square, I take fiber product, the fiber product. I assume that my category is a fiber product. So the fiber product of these two guys is going to be the collection of composable pairs of morphisms. And then we have the composition. And the composition should respect something, it should map source to substance. This source should be this source, and this target should be this target. But now I don't want to write it, I just want to write the structure, so without the axioms. So the structure is two maps and additional matrices. Oh, and maybe to be nice, I also have the identity section that for each object give you the identity of this object. So this is the structure. And now I need to write the axiom, and I want to. So there is a good way to do it by writing, or the hard way to do it by writing all the commutative diagrams that we have to write, and then there is a lazy way. And the lazy way works like this. And so write the definition. Boy object. So this data, source, target, identity, and condition, type of that, or any S in C, over. So more. Yes, over. More. Yes, more. Here we have S upper star, T upper star. So corresponding maps between composition with S source and S in background. The position with source and the target maps.
Or it's your object.
No. This is an object. Yes.
So when you write or from Y to 4.
Sorry. How I'm going to do it? Let's call it M. Don't like it, but this is more in the category C, yes.
So you write more C from Y to. So M is your object.
Object is going to be the collection of morphisms in my group. And this more is just simple-minded morphisms, which is a set. So you have two maps from like the source and the target map give you two maps like this. And
So object ob is a subcollection of objects of C, right?
ob is subcollection. No, ob is an object in C. A groupoid object in C, the idea is that the collection of all objects in our groupoid object going to be a single object in C. This is the idea of the notion of groupoid object somewhere. Like when you do group object somewhere, your entire group going to be a single object in C. So group object in topological spaces, it is a topological space, a single topological space with a notion of product, yes. And groupoid object in topological space is a pair of the topological space O and topological space M, which is better to call it more, but let's call it now. That both of them going to represent the collection of all objects, so the points now going to be objects, and M and points in M going to be morphism between two objects. And so we have here source, we have here target, and we have here the composition map, which I don't want to write. And we want this thing to be such that so I don't need to write the axioms because I just say that this is all the axioms are written.
Sir, but do you mean when you say more from Y to O?
So ob is an object in C. So all this,
Ah,
the argument
oh, it's an object with C.
and M is an object in C.
So you have all the morphisms from Y to some object. C. Okay.
And M is an object in C. And guess this is it. And another way to see it, like to do it like we did in
So to be clear, for any pair of objects and two morphisms between them, you say that this pair with pair of morphisms is one object.
is a groupoid object. A groupoid object is this data pair M of these two guys and composition. Sorry, five pieces of it.
Which composition?
It's this map for M input. And 2 is this 5 of 1.
Could you repeat how we construct morphisms between such objects? I mean, in our new category.
No, I didn't define the category of groupoid objects. I just defined what is a groupoid object. Single groupoid object.
Okay.
A groupoid object is this data.
Okay.
And you're right, here we have a serious question. What the collection of all groupoid objects, what are they? So they're going to be a two category. So we will want to define the notion of functor between two groupoid objects. And then this now, like the collection of functors between two groupoid objects, going to be a category by itself. So we want also to define a notion of morphism between two functors between two groupoid objects. I don't want to do it because there is more than one way to do it. And kind of to do it the right way, you need more structure of your original category. I will give an example instead. So for now, just I want to discuss what is a single groupoid object. So is it clear what is single groupoid object in the category C? So let me repeat.
So it should require that C has pullbacks.
Yes,
Section
yes.
square.
Yeah, that's required. You can do it without this requirement, but in the same way you can define a group object if you don't have products, but you don't like it, yes. So let's require. Yeah, so let's do maybe an example, a very concrete example. Let's work with a category of topological spaces. So, okay, not complete example. First of all, let's say the same words in category of topological spaces. So, groupoid object, topological space, or topological groupoid, is a topological space orb, is a topological space more, a continuous composition map like this, such that on the level of points, all the axioms of groupoids are satisfied. So, a groupoid object in topological spaces, it's a groupoid with a topological structure on the collection of objects and the collection of morphisms, such as the source and the target maps are continuous map, the identity section is a continuous map, and the composition map is a continuous map. Now let's do an example. If we have a topological group G, then BG is going to be a topological groupoid. We need to do a break. So let's do a break and do the example after the break. So 15 minutes break. So it means that we meet in 12:28.
לכל פרטים. בבקשה, שבה זה העובד בדור.
אני מגדיר קודם כל זוג קבוצות, ואז אני דורש שלא תהיה קטגוריה.
אוקיי.
אובייקט גרופואידי זה דאטה מהסוג הזה בקטגוריה, כך שבכל Y הדיאגרמה הזאת תיתן לך קטגוריה. או, נראה גרופואידי. אני כנראה גם צריך את ה... So I probably need also the inverse map. We also have an inverse map. I don't just want to say that the inverse exists, I want it to be a morphism in the category.
Can you see what is a composition map from the universal properties composition square?
No, I cannot. Composition map is additional data. Like, it's not enough, in order to define a category, it's not enough to have two sets and source and target morphisms. You need also notion of composition. It's not like given by the source and the target. But the composition should not be defined for any two morphisms. It should be defined on a pair of composable.
Okay. Oh, אופס. אם אתה בוחר privacy,
אני רק רוצה להגיד מה המטרה של כל אחד. זה הדרך העצלנית.
אני לא כזה מבינה.
בוא נעצור רגע לפני אחד. מה שקורה כאן את מבינה? גרופויד אובייקט זה המידע אובייקט M, אובייקט O, זוג העתקות, עוד העתקה כזאת, עוד העתקה כזאת ועוד העתקה כזאת. זאת אומרת, הרבה דאטה. עכשיו, איך זה בכלל קשור לגרופויד?
זה אובייקט אחד.
לא, זה הדאטה הבאה. גרופויד אובייקט זה לא אובייקט אחד, זה כל הדאטה הזאת. זוג אובייקטים ומיליון אלפים. 4, לא יודע, 5.
אז זה זוג אובייקטים ב-C.
כן, גרופויד אובייקט זה זוג אובייקטים. מה זה גרופויד? גרופויד זה שתי קבוצות, קבוצת אובייקטים וקבוצת מורפיזמים, העתקת הסורס והטארגט ביניהם, העתקת הזהות, זאת אומרת חתך הזהות לכל אובייקט, יש לנו את הזהות שלו, זאת אומרת העתקה מקבוצת האובייקטים לקבוצת האלגוריתמים, והעתקת הקומפוזיציה, שלוקחת זוגות של אובייקטים הניתנים להרכבה, ומתאימה להם. זוגות של מורפיזמים ניתנים להרכבה, ומתאימה להם מורפיזמים. אבל אז יש אקסיומות, אני לא יכול סתם להגיד. עכשיו, אני זוכר את האקסיומות, ועוד יש את העתקת האיפורים לכל אקסיומות. אני יכול לשבת לכתוב את כל האקסיומות האלה. אבל אם נכתוב את האקסיומות האלה, איך אנחנו בגיל כותבים אותם? אנחנו כותבים אותם כמתים, כן? לכל אובייקט, לכל כזה. עכשיו, אסור לי להשתמש בכמתים. כי אין לי אובייקטים, יש לי אוסף כל אובייקט. זה לא נורא. כל אחת מהאקסיומות אני יכול לשבת ולכתוב אותה בתור דיאגרמה כמותית. כמו שאסוציאטיביות בחבורה. כותב את זה עם כמתים, נכון? לכל X ו-Y ו-Z, ואני יכול גם לכתוב את הדיאגרמה המגוחכת. G1, 2, G, G כפול G כפול G, ועדה G כפול V, אני צריך להגיד הרבה מילים, איך הוא מועתק ל-G, וזה 1 כפול M, וזה M כפול 1, ואם להיות 100% הגדול אני יכול לפתור את זה ככה. אני צריך להסביר למה יש לי את המורפיזם הזה, זאת אומרת, אני צריך להגיד מלא מילים רק בשביל להגיד אסתטי. עכשיו פה בגרופואיד, מכיוון שיש יותר אקסיומות, אני צריך להגיד הרבה יותר מילים. אז אפשרות אחת זה לעשות את העבודה כמו שצריך, לכתוב את כל המילים האלה, לכתוב מלא דיאגרמות, להגיד שמות. אבל יש את האפשרות של הרמנים. להשתמש ביונד. במקום להגיד שאיזשהם דיאגרמות קומפוזיטיביות, אני רוצה לתרגם את השאלה לקבוצות. גרופואידים נמצאים של קבוצות. אז אני צריך לקחת טסט האובייקט, לרוץ על כל האובייקטים, בהינתן אובייקט Y, על more מ-Y ל-O, יש מבנה קבוצה. ומור מ-Y ל-M זה גם קבוצה. ושתי העתקות האלה נותנות לי שתי העתקות כאלה. של הרכבה. וגם העתקת ההרכבה נותנת לי העתקה מתאימה, אני לא רוצה לכתוב את זה. וגם העתקת האידנטיטי נותנת לי העתקת האידנטיטי, הכיוון הזה גם הרכבה. וגם העתקת האינברס נותנת לי העתקת אינברס מכאן לכאן.
ואז אתה אומר שזה גרופויד, כי גרופויד זה בעצם, כמו שאמרת, שתי קבוצות, ואור וכל ה...
זה
כן, עכשיו הבנתי.
באופן כללי בתור הקטגורית, את יודעת איך לכתוב משהו, אבל לקבוצות, את רוצה לכתוב במעברים, ואת לא יכולה, אסור לך, לכתוב כאילו אובייקט בקטגוריה, אז אפשר לנסות להתחכם, ואפשר לרמות. נשתמש ביותר. Рисовал. Так диаграмма, да? Но опять-таки это не обязательно делать, потому что можно вместо этого рассмотреть функцию, которую представляет наша группа. И там аксиома ассоциативности можно сказать, как обычно, для любого элемента. Ну вот это...
I mean in this case.
для любой элемент. Для любого элемента не хочу. Ну, можно, это будет совсем плохо. Давай попробуем.
We need to have a triple of composable morphisms, right? So it should be two.
Ну, давай три. Три повесил.
So it would be something like.
Ну, это совсем не обязательно, да? Да. Окей. И сейчас надо отображение. Сейчас у нас есть отображение отсюда. Здесь у меня положено.
Усатый получилось.
Так, это файлополе в двух вещах. Да. Так отсюда у нас есть отображение, отсюда есть отображение правильно. Потому что отсюда есть отображение не в M2, а в M помножить. Не, я думаю, это немножко оверкил. Это тоже верно, но мы можем легче.
Стартовать должны отсюда.
Да, и M3 это верно, это правильное определение M3, но оно оверкил. Думаю, легче все-таки определить M3 как M1 times M times M M2. Тут можно умножить на M1 над O. Где тут мы берем source, а тут мы берем target, а тут source. Да? M2 тоже напишем target, а тут source. И отсюда есть отображение в M1 умножить на M1 на 0, которое есть M2. Так отсюда есть отображение M2. С другой стороны, эта вещь это морфа. M2 умножить на M1 на 0. Надо доказать, что они морфы, надо строить измерчитель.
Собственно, вот это, видимо, произведем вот эту, вот это целое, вот это.
Ну, действительно, язык представляет функцию, он значительно легче в этом случае, да? Весь трюк, чтобы мы не хотим это делать, из этого мы просто говорим, что функция, которая представляет нашу группу рядов, наша пара, наша дата, если мы берем эти функции, тогда значения будут.
But don't we want don't we want about I don't understand about target and source. Don't we want that target and source would be same object anytime? Don't we?
They're not objects, they're more
Yeah, I mean that when we have some monoid, then target and close for any arrow
We're talking about groupoids.
groupoids. So when we have some groupoid, any arrow has same source and target, doesn't it?
No. Two different objects might have multiple groupoids. Sometimes we choose any groupoid is equivalent to a groupoid such as any object we have.
Okay, yeah.
And this is correct, but it's not correct in groupoid object in some geometric theory.
So we can think about it like co-product of such.
Yeah, exactly. So this I will try now to explain why where it breaks down.
Yeah.
Yeah, well, if I can't really explain because I didn't define what are equivalent of groupoid objects. It's not. It's great. So I can you can do something rather easy, but this can will not really give you the quite enough.
אולי זה ספר פרטי.
So we have another half a minute.
אז יש פה סופר פאוור שאני לא יכול ללמוד גם ככה. אני לא יודע אם יש אנשים אחרים. זה אש, אמרת על זה?
So I think we should select.
I didn't share that with about the beacon.
כן, אבל
קרינה שאתה אומר שזה חשוב.
Okay. So groupoid. So I want to give an example, but before the example, questions? Let me give an example, maybe it makes sense. Topological space. So we gave one example, BG. The first one, let me give this example. Formally, so in BG, the orb is 1 point, and the mode is just a group G. And of course, the source and the target map are the only maps set to XB. And the identity section is the map that sends a single object to the neutral element G. And okay, the fiber product over orb source targets is all the same, it's just product G times G, so the composition map is just a multiplication structure on the group. But now everything happens in some category, so topological spaces, sorry. So in the category of topological spaces, so it means that G have to be a topological space. The product structure has to be continuous, and the multiplications map have to be continuous. Multiplication map, which is the composition in the groupoid. This of course continuous because it's 1 point, and the inversion map from G to G has to be continuous. I'm not sure it's automatic when we define general topological.
So it's a topological.
So it's just topological. So if G is a topological group, then what you get here is a group. Topological group. Now let's do quotient groupoid. We have G acting on X, and we want to describe the groupoid X modulation. And before we describe it, but like point-wise, we said points are elements in X, and morphisms are elements in G that maps 1 to point 1. But now we're forbidden to talk about points, we need to talk about collections. So the collection of all objects is certain X is easy, but what is more? The collection of all morphisms, not from one point to another, but of all morphisms. No guesses? Let's make it easier. What is the collection of all morphisms that starts with a single point, with specific point x? Exactly. Because we don't have any more the conditions that it have to map this point to some specific point. We just have to map it somewhere. So collection of all morphisms that start with a specific point x is going to be G. So what's going to be the collection of all morphisms at all? X times G, exactly. And what going to be the source and the target map? So one of them is easier than the other in this relation.
And it's just a projection.
So the source is just a projection to the first coordinate, because our convention was that we consider such a pair like a point x and then arrow G that goes from this point somewhere. But what's the target?
Action.
The action map. The action map is a map that map pair Gx to Gx on x. So if we have an action of G on x, we get two maps, projection and action, and this forms, I need to define more things, but basically this forms a groupoid object in topological spaces. So I need to define the identity section, which is easy, just x going to x comma identity. I need to find the inversion, okay, this is also easy. And composition is a bit annoying, but let's do it. X times G over X. Here we take projection, and here we take action. So we have a pair of elements, such as the first element going to be the action on the result of the action on the second element. We have pair here and a pair here, and x1, g1, x2, g2, and we take all this data, but x2 going to g2 times x2 going to be x1. So x1 becomes obsolete, and the product is canonically isomorphic to this. So x2, g1, g2. And what are these two maps? This is going to be projection on the first two coordinates, and this is going to be action on, like, taking action here, and then don't touch the last coordinate. And now we have to have as a composition map from here to more, which is just x times g. And any guesses what it's going to be? Fucking sure, I have two guesses.
You want N3
This was one of my guesses, and the other guess is just action on the first two, and I think that you are right. So the first guess is correct because this action is already here, yes. So we have to have something new. The G1 times G2, that makes sense. So if we have morphism that starts with x1 and goes to projection is a source, yeah. So it starts with x1, goes to G1 times x, and then the pair of components will move them, but for the other way around. So we have x2, x1, and g. This is g2, this is g1, g1 times x1. So we want to compose them, so we don't touch x2, and we compose here g1 times g2. This is the correct direction somehow. We first apply G2, then apply G1. So the morphism here is just smash those two guys. So we have all the three guys here somehow. Here we have smashing these two guys together. Here we have just projection on these two guys. And here we have smashing these last two guys together. So this is a quotient groupoid. If we have a group, the topological group is G acting on topological space X, so in any category, a group object in a category acting on a group object in an object, One has to define what it even means, group object acting on an object. So this is what it basically means, that this thing will give you a group point. But in topological spaces, we see that something non-trivial happens. So let's take, for example, the group, multiplicative group of the line R times acting on the actual. We have two orbits. So it means that this groupoid will have two isomorphism classes. 0, the origin, and everything else. And if we forget about the topology, then this groupoid is a coproduct of two groupoids, one which is a BR or BR star, BR cos, and the other which is a trivial groupoid, B trivial. As a large orbit becomes a trivial groupoid because the stabilizer is trivial, and the small orbit is now the complicated thing because it's a non-trivial stabilizer. But these two things are glued together. The topology knows about it. When you take the coproduct, it will not know about it. So I didn't define what are equivalent topological groupoids, and I didn't define what is a coproduct of topological groupoid, but you already from this example, without knowing what are the definitions, you don't really care. You see that it's not going to happen. Those two things are going to be very different. Because R and this disconnected union of a point with a complement to a point are very different. So this theorem that all groupoids are coproducts of BGs are not true anymore. Now I will give you another example of two things that we do want them to be equivalent, and we will see that why it's not trivial to define what are equivalent topology objects. Oh, you have more than one option to do it then. It's not clear with me. So if you have a topological space, and we explained that if you have a topological group, then you can construct a groupoid out. But also if you have a topological space, you can construct a topological groupoid out of it. Just you take the space as orb, and more just equal to orb, and you have only identity. So this is kind of the stupid category that you can do, but in topological space. So let's take a C star, a C cos, the plane without the origin. This is the topological space, and we have other two times also, and here we have just identity. So this is a very stupid topological groupoid. And now let us take more complicated topological groupoid. Yeah, let's see whether you know how to say it. So we take two copies of C cos, take the union, and then have two maps here. One will be identity half identity, meaning both of the copies just go to itself. And the second will be identity half Z goes to Z squared. So it looks confusing. Let's see what we actually have. We actually have on the level of objects. Yeah? So each point here gives you an object. And then this object has two morphisms that are going out. Yeah, because this is a source, so the two morphisms just named by the same object, but the target going to be different. One of them going to be the identity morphism, target going to be the which else. And the other, no, it didn't do it correctly. It's not what they wanted. No, they're going to the square. They're going to minus it. And the other going to the target going to be minus it. And that is for itself. Yes. So guys here we call identity, and the guys here we call S. And for each object, each element in C star will have the identity map and the negative map. So from topological point of view, the collection of isomorphism classes, what is going to be?
For each isomorphism class, they'll have a set and
Yes. So all pairs of complex number and it's negative. And do we have non-trivial automorphisms?
זה Z minus C,
לפי אתה אוכל אותה? What?
Z minus C.
Z to minus Z, but it's not automorphism. It's morphism between two different elements. And
I have the same thing.
same thing. So do we have non-trivial automorphism? Automorphisms which are not identity? We don't, yes? Because by definition, S is not identity. We excluded zero exactly because this is, yes? So no non-trivial automorphism. What does it mean? So as a abstract groupoid, not a topological groupoid, it's going to be union over all pairs Z minus Z, and each of them is an equivalent groupoid to the trivial group. We have to the trivial one, BG, but trivial group G. Because you can choose an item representative and just consider it automorphic. But what is this collection of pairs of complex numbers Z and minus Z?
Projective complex.
I don't know lines, just pairs Z and minus Z. These are some invariant of a complex number that you can take a complex number which kind of will not distinguish between Z and minus Z, but will distinguish everything else. Square. So in fact, there is a natural bijection between the collection of pairs of complex numbers, one Z and minus Z, and just complex numbers. Yeah, it's, you know sometimes.
It's a bijection.
Oh, no. Without zero.
But it's not a bijection because
Between the collection of pairs.
Okay.
So the isomorphism classes of this groupoid going to be bijection to the isomorphism class of this groupoid. But you can say it's stupid question statement. Everything is of cardinality aleph, of the continuum cardinality, so everything is bijective, but this is not just a bijection. Very natural, nice, but bijection is a continuous map. So we have a continuous map from here to here. And then goes to Z squared. And this continuous map kind of become a functor of the groupoids. So what do we do to the so here we just fold them one with the other. The identity map becomes the identity map, but the other map, the S, also becomes the identity map. So when we consider them just as an abstract groupoid, we have a functor which is an equivalence contiguous because it's fully faithful and essentially surjective. Very easy exercise. F is equivalence of so abstracts are equivalent groupoids, not like topological groupoids, but like groupoids are equivalent groupoids. The same, like here we had that this groupoid was equivalent to BG and B, sorry, BR times co-product with. But it's not really the same because here there was abstractly equivalent, but this equivalence was not coming from anything continuous. And here we do have a continuous map, continuous functor, continuous map, but also continuous map here, and the satisfy the axiom of functors to one direction. But to construct the function to other direction, we need to use this theorem that fully faithful and essentially surjective is equivalent. Now we don't really need to use this theorem of choice here, or the axiom of choice here. All we need to do is to choose a square root, which you don't really need axiom of choice, but you can do it in a continuous way. So you can fairly ask whether these two topological groupoids going to be equivalent as topological groupoids. And there is no one good answer. Depends how you define the two category of topological groupoid. But often you want them to be the same. And this means that these two categories have to be defined in some complicated way, because just a naive way just saying that functor is going to be just continuous map which give you a functor, not going to be enough. And before, you remember when we talked about quotient groupoids? Yeah, by the way, this is a special case of a quotient groupoid. Here you have the group S2 acting on C star by multiplying by plus or minus 1. Yes, S2 have two elements, bigger one at the identity and other one at the multiplication by -1. And when you take the quotient groupoid, S2, it's not a subgroup quotient, it's quotient by an action. You see that you exactly get it. Yes, this is O and mode is S2 times C star. And the two maps going to be the projection and the action. So exactly for quotient groupoid. So you often have quotient groupoid which are equivalent, and we said that even in topological settings, when you have equivalent groupoids, you get similar answers, the same answers or equivalent answers to many questions, which are actually not depends, which you think, or you might think that depend on the pair G times X, but in fact it depends on only on the groupoid. But if you want it to be powerful enough, you also want to say that in such cases they will give the same answer. So you need some weaker notion of the collection, like of equivalence of groupoids, that will allow these two things to be equivalent. Because if you look at all the examples that we had before, like H1, G, H2, and all its friends, say 1, G, H1, G, H2, G. So for example, this equivalence, so after group is correct. For topological group, we said that we have its natural only to one direction, and the other direction we don't have a natural map. We can choose, but we don't have anything natural. And in this case, when everything is topological, so natural become continuous, and non-natural become discontinuous. So these things will be equivalent as groupoids, but only with respect to some weaker notions that allow you to revert things which are fully faithful and such as objective. And sometimes it's even worse. Sometimes you have to compose several procedures, and each of them go to another direction, and then there is no natural procedure, any natural procedure to any direction. And on the technical level, there is no continuous procedure. There is no continuous move to any direction, and yet you want to think about them as the same because you can identify them with using several continuous procedure, but each of them is continuous only to one direction. And there's a way to do it, but probably not for this time. Oh, and they even have 10 minutes left. So questions about topological groupoids? No questions?
Okay, you said that we have an equivalence of groupoids, like trivial groupoid C star, equivalent as an abstract groupoid without the initial structure to C star quotient by SS2.
Yes.
But they are not equivalent as a topological groupoid.
I didn't say that they're not equivalent because it depends on the definition of equivalence of topological groupoids. So with respect to some of them they will and some of them will not. In the naive definition,
naive definition.
So
we don't have inverse map.
Yeah, but there is a functor which is fully faithful and continuous functor, continuous in the sense that is coming from continuous map, which is fully faithful and essentially subjective, but the inverse not going to be continuous.
Oh, okay, yeah.
It's going to exist at the level of sets, but not on the level of.
The inverse is not. No, but if it's on the level of pairs, it is continuous, no?
Exactly, but the set of objects is C star.
Mm-hmm.
It's not pairs. On the level of isomorphism classes, you can identify them, but it's even better than that. You can you actually have a map which is not just by injection isomorphism classes. It's a fully faithful and essentially subjective factor. It really wants to be equivalence of categories, but technically it's with respect to. It is equivalence of categories, but not equivalence of continuous groupoids with respect to topological groupoids with respect to one of the definitions. So this topological groupoid is not very common. We usually will not see it. So first of all, it's much more common to do it in the setting of algebraic varieties. And so algebraic variety groupoid is called often called algebraic stack, but when people say algebraic stack, then they actually do mean that these two things are equivalent. They have a different definition of functors between algebraic stacks and what it's mean to be equivalent, and then these two things are equivalent, but it's harder to define. Oh, so one thing that I didn't say, and but it's kind of obvious, that if you have 3 employees, gamma 1, gamma 2, gamma 3, beta, and then you do first perform beta star, and then perform alpha star. This functor is canonically isomorphic to first perform alpha and perform beta. And then, of course, you have the adjunction commute with composition, so you have the same thing for lower stars. Better star. Star, and similarly for Roche. Not so much. And something which is more surprising is base change. So it's something very general in this world of, it's sometimes called the six functor formalism, or quadratic functor formalism. If you have some geometric objects, in our case, geometric objects will be not so geometric, it would be groupoid. And then you have some algebraic objects that you attach to this geometric object. In our case, it will be representations of groupoids. And you have map between the geometric objects, and you often can pull and push. And sometimes, so in the more general setting, each of the operations, both pull and push, you can do with 2 versions, a star version and a Schrick version. And then there's some junction. Here we don't see it because here the pull is just one version, the star version and the Schrick version are the same, so simpler. And then you have something that's called base change. So let's see, x, y. First, I'm going to say you have it, so it's not a theorem, so it's something that you expect to have, and sometimes you can prove it, sometimes you can construct it, or whatever. And what is the idea here? And you have an object here, and the idea is that you want to push it down here and then pull it back to here. And you can do it equivalently by first pull it back here and then push it down. So it depends how you pull it and how you push it, but the idea is that it should be the same. How should we think about it in general? Okay, so maybe something that I should have said long before. There is this idea that's called Grothendieck's relative approach, relative whatever, something approach, point of view, whatever. That if you study category C or study some geometric objects of certain type, everything that you can ask on these objects, you can also try to ask for families of objects. So first thing that you have to do, you have to define what are family of objects. And the idea is that given a category C, families of object parameterized in an object X is an overcategory of X. And if your category is kind of geometric category, so you have a notion of points in X, then, or the tightest have a notion of points in X, then how does object in the over category gives you a family of objects? The idea is that for any point in X, so point in X you can consider that a map of some point object to X, and any object over X, you can construct the fiber product. The fiber product in geometric corresponds just to the fiber if X is kind of a point. And then family of objects over X actually give you family of object in the over category actually give you family of objects. And although usually you don't have one, no, sometimes you have an object which is 1 point, but sometimes you don't. You don't really have to have such an object because you can put here any object in the category and do this fiber product. And what is the map from? And then you come to this unit situation. Yes, so for any object S, you have this set of morphisms from S to X, which you can think about as Sx. Yeah, because X is represented by this. Oh, sorry, it represents a functor, which is for any S, this collection of morphisms from S to X. So for single X, this collection is not enough to get all the information on X, but if you arrange over all S, it is enough. And then it kind of makes sense to think about an object in the over category as a family, even if you don't have a natural point. But then you come to a very natural thing to do. So you have an object here on Y, and you want to push it down to X. And then, but you remember, you think about object in Y as family of object parameterized by the point in X. So you have lots of objects here. For each Yx, you have something over Yx. And then you want to push each of them down. So you can take each of those guys and push it down. But now we want to do it in one big family. So how to think about the Yx is family of objects, but now we have family of objects over each Yx. How to think of them of one big object? You think of them as an object in Y. And what is the relation? We start with object in Y, and you can pull it back here, and then get an object for each Yx. So you can pull it back here and then push it, so you get an object over X. So if X is a point, so object over X is going to be something very simple, but not vector space is stupid. But the other way around, you can push it here, you get object over X, which also you can think about as a family of vector spaces if your object is a sheaf or something like this. And then you can pull it back to X. This is the way you get the family for each point, you can pull it back to the point. And you want it to be the same, because otherwise it means that you cannot think about an object over Y as a family of objects for Y for each X, or objects over Yx for each X. Or at least you cannot do it when you talk about push. And if it is the same, then you satisfy the base change. And the thing is with the base change that it usually does not work naively. So if you will pull and push in the same method, then it will not work. So as I say, here we have one method to pull, but two different methods to push with star and shrink. And you have to choose. If you on the horizontal line choose a star, then vertical line is you have to choose a shrink, and the other way around. So here it's a bit easier, and so here probably you can just do the yes, since the pullback is both star and shrink, it means that you can do whatever you want on the vertical line and it will work. But this is not a typical thing, it's typical for this situation of groupoids, which is kind of set theoretical, very discrete, so it's not topological groupoids. So let's write it down. So now theorem. Break. And if we have a Cartesian square of 2 points, let be square of 2 points. And V Z. Now names pi, tau, alpha, beta. Then pi over tau of V. And then we take beta out of tau. This canonically isomorphic. We first take alpha out of tau of V. And then take tau. And the lower stars we allow also to replace by shrinks. But of course we can't do either one or the other. So either both of those are star or both of those are strings.
What is F?
F, I don't see F. Where is-
It's down again.
This, oh,
No, on the other side.
this part.
Right.
So push and then pull is the same as pull and then push. So the Cartesian square somehow looks symmetric with respect to like flip by 45 degrees, but when you do base change or when you think about this statement, better not think about them as symmetric because this is we can think about this as object in the over category of X. So family of objects parameterized by X. And the pullback means that we have a family parameterized by X. So the Cartesian square diagram of pullback of maps, yes. It means that instead of family parameterized by X, you do reparameterization by Y. But if you have a map from Y to X, it means that it gives you a way to do reparameterization of the family. So basically, W over Y is the same family, but parameterized over Y. So it might not be the same, it might be smaller because the map is not onto, but if the map is onto, it's kind of the same thing. And what we say here is that we can just push here and then do the reparameterization, or do the reparameterization and then push. So it means that this procedure of push makes sense in family. So maybe the extreme case of procedure of push, if you have terminal object, so the point is not really the case, but never mind. If you have terminal object, then then the extreme case of procedure of push is just push to a point, which is kind of the integration of your family of your like whatever object on the entire X. And now you have family of objects. And what is push in general? If the map in general, you think about a family of objects. So push is kind of integration done for each element if each member of the family. So we start with a representation of say group point X, we can integrate it and then we can push it and get a representation of Y, which means that for any point of Y, we get basically a vector space. Yes, what we are doing there. Function of vector space. So push is kind of integration for any member of the family, and you collect all the answers together with one object over one. And this Cartesian square means that this kind of makes sense. That when if y will be y here is a point, then you can push to x, and then sample your result in a point. The same like sample your family over a point, and then push like the integration of this point. Maybe next time we'll start with just repeating everything here, but for plain sets, the points and everything will match. Simple. We should start with this class. Okay.
Last equivalence.
I didn't
A
focus.
theorem or
Theorem. For the points is theorem. Both of them did, and the same with shapes. Okay. This is it. Yeah. Let's see how stuff. But I didn't prove it. I will probably prove it next time. It's not hard theorem, as usual. But sometimes in other settings it can be very hard. But this, I will start with doing it for sets, and then it's kind of obvious theorem. More questions? More questions?
You maybe give an example or a reference.
Example I would be given next time. About of them, hopefully. And reference from in this context of points. So in other contexts, there are lots of references.
Generally, families.
Of God in the of the relative point of view. And plenty of them, yes. But,
I didn't really understand what you meant when you said base change.
so base change diagram is a Cartesian square diagram, just nothing else. But when we say base change diagram, it means that you think about Cartesian square diagram from a certain point of view. And first of all, the Cartesian square is something which is very symmetrical, but when they call it base change, we don't think about it something symmetrical. We think it's a very different role for vertical maps and the horizontal maps. The vertical maps, we think about them as a family of objects. And the base are the objects downstairs, the base is the parameter set. And we think about this family as a reparameterization. This is why it's called base change. You change the parameter set, you change the base of this family. And this theorem also sometimes called base change. It means that in case of reparameterization, you have the reparameterization commute with push. Usually it's in context of usual categories. Here we're talking about, I mean that all these diagrams should be diagram in a category. Now this diagram is not diagram in a category. This diagram is diagram of group points, it's diagram of two categories. So it's kind of more complicated than the standard base change, but it's much easier because we take just the simplest possible object, the simplest possible two category, which is a two category of group points. It's even simpler than the two category of category. But we can start next time with doing it with the simplest possible category, which is a category of sets. And then everything will be very simple.
So if you could give an example
For sets?
No, for group weight.
Yeah, so you can, well, this will be next time, but I can start now. Well, let's start with sets. Sets is an example of group weight. You take a set of 10 elements here, and then say over each point of the set you put like 5 points and 6 points and I don't know, whatever number of points you want. And here you can start with 1 point. And then when you take the base change, it means that you can sample 1 point. This is one way to do it. Another way to do it is, or another example is to take some reparameterization of this set of 10 points. So we can count it backwards. Or you just count each point twice. But let's do it next time. It's